Okay, now any questions? No questions? I find that troubling. No one had a problem with number 7? Yes? 17? Okay, 17 is summation n equals 1 to infinity. 1 plus 2 to the n over 3 to the n. All right. So when you're looking at this, hopefully you see that you have your index n is controlling the exponent, which is usually what happens when you have geometric series. And so what we're trying to see is maybe we can make it look like summation a r to the, we used, what, k minus 1? That will equal, well, one of two things. It converges or diverges. It converges if r is less than 1, magnitude of r is less than 1, converges to a over 1 minus r, and diverges if r is 1 or greater. So can we do this? Well, the problem is the 1 up here, right? If this were just 2 to the n over 3 to the n, you could just put 2/3 to the n. So what I can do instead is I can split this up into two fractions. So I put the 1 over the 3 to the n, and then I say plus the 2 to the n over 3 to the n, like that. That's just algebra, right? Splitting it into two fractions. And then each one of these, I can write those as, let's see, 1/3 to the n here, and then over here I can say 2/3 to the n. You agree with that? Now, by itself, this right here looks geometric. I have like an r to the n, not n minus 1, but I can make that happen. This again is an r n minus 1 I can make happen. The r that I would have for each of these would be less than 1. So I have two different r's, right? So what we're trying to see is that this is a geometric series, but it's actually two of them. So the question is, what can you do? I believe I mentioned that on in class last time. Yes, but I'm looking. I don't think I did mention it, actually. Seven to 13. What are you talking about? As far as the problems I assigned? Oh, I don't know. Did I assign 17? Okay. Yeah. Oh, yeah. Did I point out the here's what I was getting at. Did I point out the properties of the summations on page 441? Did I put that in the notes? I did not say anything about that? Maybe I just hadn't gotten to it yet. Okay, well, I'm going to reference it now. We'll talk about it a little bit more later. But your assumption is probably correct here that if you have the sum of two series, right, the sum of two separate things, that you can break it into two separate sums. And that's all given to you on page 441 in a theorem number 8 on that page. Okay, so I'm going to use that to break this into two summations. This first one, I'm going to write it as n minus 1, and then to the 1, or times 1/3 here to the first power. So just remember, we subtracted and added 1 up here, and then the minus 1 goes here, and then the plus 1 we turn into a different factor. Did I do that enough last class for you all to be comfortable with that? Yes? Okay, that's the first sum. Now the second sum, I go plus. Now the second sum, n equals 1 to infinity of what, 2/3 to the n minus 1, again, times 2/3 to the first power, which I don't need to write that first power. And so both of these are geometric series. They both converge because they both have r's that are smaller than 1. So the r here is 1/3, and the A here is 1/3. Over here, the R is 2/3, and the A here is 2/3. So let's just figure out what this adds up to be. It should be A over 1 minus R, right? The first one here should add up to be A over 1 minus R. So A is 1/3 to the 1 minus R, which is 1/3 again. Then I have plus the other one, which is again the A here, which is 2/3 over 1 minus R, which is 2/3. So I'm going to get two fractions here. Let's see, this is 1/3 divided by 2/3. What's 1/3 divided by 2/3? 1/2. I'm doing 1/3 divided by 2/3. Flip it, right? Flip this up, it becomes 1/2. This one is 2/3 divided by 1/3, and that's going to turn into what? 2. So you get 1/2 plus 2, which is 5/2. Was that the one you asked me about also? Okay. It looks familiar. I'm willing to talk about one more. If there are any. 25. Did I assign 25? No? Okay, then can you wait? Because 25, I haven't talked about how to do it. Which one? Which other one? No? Did I assign 19? I did? Oh, okay, yeah. All right. So it's summation and goes from 1 to infinity of the nth root of 2. Is that it? So what does it mean to take the nth root of 2? It's 2 to the 1 over n, right? It's 2 to the 1 over n. That's what that means. So let's look at this right here. Let's not look at the series. Let's look at the sequence. The sequence here, a sub n, is 2 to the 1 over n. What does that series converge to? What does the sequence, what does that sequence converge to? As n goes to infinity, right? This goes to 1 over infinity, goes to 0. 2 to the 0 goes to 1. So this thing is approaching 2 to the 0, which is getting closer to 1, right? So what happens, what did we say last class, if your sequence of terms converges to something other than 0? The series diverges. What's happening is each one of these is getting closer and closer and closer to 1, which means you're just stacking something really close to 1 on top of something really close to 1 on top, and you're adding them up. That's going to diverge. It's going to become infinite. That make sense? So this we're doing by just investigating the sequence. And that's really all we have up to this point. Well, we investigate the sequence. If it goes to something other than 0, we know that the series diverges. If it goes to 0, what does that tell us? It could diverge or converge. We don't know. But if it's not 0, definitely diverges. The series diverges. That's called the Nth Term Test. I'm going to write that down formally today. Then we have geometric, and then I ended with harmonic. That was the last thing I started talking about. All right, so that's where I'd like to pick up harmonic series. We'll just do an example of a harmonic. Just FYI, my daughter had a procedure this morning, and depending on her level of comfort or discomfort, I may or may not be in my office after class. I'm going to call my parents, see how she's doing. If she's in a lot of pain still, I'm going to go, she wants daddy, you know, that sort of thing. So hopefully the painkillers will have kicked in by then, and she'll be all right, and, you know, I'll be around. But if you come by my office and I'm not there, just FYI, I'm giving you some heads up first. Okay, harmonic series, we said last time, there's different ways you could write it, but you basically have an index, and that index is going to infinity, and then you have some constant. Now, I don't recall if I used C or A. I used A. Okay, A over N. And the big thing is that your denominator is growing, right? But it's linear. In other words, it goes up 1, and then the next time it's 2, and the next time it's 3. So that's a linear change. Every step, every term in the sequence is growing. The denominator is growing by some constant integer power, like integer. Does that kind of make sense? So if I wrote this out, this would be like A over 1 plus A over 2 plus A over 3 forever. If you ever have this happening, guaranteed all harmonic series diverge, become infinite. So this will always diverge. So I'll give you an example of this that may not be as obvious as anything I've shown you. So how about if we're trying to add up, if I say take 1/4 plus 1/8 plus 1/12 plus 1/16 forever. So find that sum. So maybe you first look at this and you say, okay, 4 is 2 squared. This is 2 cubed, I agree. But 12 is not 2 to the 4th, right? So I'm thinking maybe initially it might have been like geometric, where you had 2 to a power, 2 to a power, 2 to a power. Do y'all see that? So what else? Do you see what it could be here? 4, they're all multiples of 4, right? This first one is 4 times 1. This is 4 times 2. This is 4 times 3. This is 4 times 4. So they're all multiples of n, not powers of, they're all multiples of 4, not powers of 2. So maybe I can write it this way. Sum n equals 1 to infinity of 1 over, how do I say multiples of 4? 4n. And you could just check, plug in, just make sure that that looks okay. Is that a geometric series? No, because the exponent, or the index is not in the exponent. So we start thinking perhaps it's harmonic. Well, for it to be harmonic, it has to look something like this. Is it? The 4 is the only issue, right? So could I write it like this? I mean, you could write that as 1/4 times 1 over n, couldn't you? Pardon? Good. I'm glad. Yes. So, and then going back to that page 441, the theorem tells us that if we have a constant inside of a series, that constant can come out. So if I pull that 1/4 out, and when we say pull out, it would be pulled out as multiplication. So times sum n equals 1 to infinity of 1 over n. And now that last piece, right, that last series here, diverges. Now we do run into a little bit of an issue here, because on that theorem, okay, this is kind of important, I want to point this out. On the theorem, it says, I'm referring to page 441, it says if the series A sub n and B sub n are convergent, then these properties work. See, but this is not convergent. So can we still pull out the constant? According to the theorem, we're not guaranteed that that'll happen. All right? But I could have left the 1/4 inside. I could have, and just rewritten this. I mean, isn't this the same thing? How can I rewrite 1/4 as something on top? How about just like 1/4 over n? Isn't that the same thing as this? It's the same thing, right? So that's like our A over N. So it works the same way, and that's harmonic and it diverges. So just be careful on this right here, that this property will only work if this series must converge for that to work, okay? Converge, not diverge. And this one doesn't converge. But by doing it this way, it's okay. We don't need to pull the constant out. Do you understand what I'm saying? So what's the result? I mean, what's our conclusion here? Diverges. All right, let's talk about a series real quick that we haven't looked at yet. It's not really addressed in the book, like they don't give it a name, but I'd like for you to tell me what happens here. What would happen if I say sum n equals 1, and this time I'm going to stop it. I'm going to stop this at, let's say, some constant, n, c, of 1. What is this? This is going to come up later, so I was thinking about it, so I might as well throw it out there. What is this? What happens if you let n be 1? What do you, if n is 1, what do you put here? 1, right? It's just 1, so I do 1. Then plus, now I let n be 2, right? And it's still 1. And then I let n be 3 and keep going, right? And I get 1 again. And I keep doing this, and I stop eventually, right, at c. How many of these will I have? How many of these will I have? There will be c of them, right? So won't this just be c? So if you take the sum, n equals 1 to c of 1, the answer is c. And later on, when we get to a problem like this, we will have something like this. We will actually just jump from here to the answer, and I won't go into the detail. I'll just say, oh, remember we did that in class? We can show that that's true. What would happen if I changed it and I went n equals 1 to c of a constant a? That'd be a plus a plus a plus a plus a. How many of them? C of them. So this would be AC, a times c. So you just take this constant and multiply it times this constant, and you would get a times c. That make sense? All right. It's kind of off the topic, but all right. So let's talk about now our next type of series. Remember, there were 3 that we wanted to talk about in this section. Telescopic was the one we hadn't talked about. This is also referred to as a collapsing series. These are kind of tough. Okay, so check this out. Let's take a series that looks like this. We're going to start, the best way to do this was with an example, and I'm going to start with a fresh page. Make sure you got plenty of room, all right? Because it's going to take a little bit to get this. All right, I want to do sum. I'll use k instead of n. K equals 1 to infinity of 1 over k times k plus 1. So let's think about a few of the things that we have up to this point. We have checking to see what happens to the sequence, right? Seeing what that goes to. If that goes to something other than 0, we can say it diverges right away. We have the geometric series and we have the harmonic, right? That's what we pretty much have at this point. So does this look geometric to you? No, right? Because the k is not in an exponent. Does it look harmonic? Kind of though, right? I mean, like the 1 over k, that's like 1 over n, right? The problem is I have another one next to it. And so when you multiply those two together on the bottom, k times k plus 1, it's not linear anymore, right? It's quadratic. And I said that the harmonic works because the denominator is linear. It's jumping up each time by the same amount. Here, it's growing quadratically in the denominator. So maybe it converges. What if I were to look at the sequence? And I'll write it a sub k instead of a sub n. It's 1 over k times k plus 1. So I'm looking at that right now. I'm taking the limit as k goes to infinity. Where does that go if k goes to infinity? It goes to 0, right? That goes to 1 over infinity, which goes to 0. And what's my conclusion? If I look at the sequence and the limit of the sequence goes to 0, what's our conclusion? You don't know, right? It's basically you don't know, right? It's inconclusive, all right? So we know it's not geometric. We think it's not harmonic, and it definitely does not pass that test. It's inconclusive. So we have this new type of series, and it's called telescopic or collapsing. But to see it, we have to be able to do something here that we may not have. Well, we haven't done it in a while, but we have done it. Partial fraction decomposition. Remember we did this for integration. When you had integrals and you had this, we said we could rewrite this, and you'd put like a over k plus b over k plus 1. Don't remember that? You're going to have to go back, look it up if you don't. We're going to do partial fraction decomposition to get from this step to the next step, and I'm not going to show the work. I'm just going to tell you what it is, but you have to realize that there would be work you would have to do here. This decomposes into 1 over k minus 1 over k plus 1. So that step from here to here is partial fractions. Partial fraction decomposition. Y'all know what I'm talking about there? I mean, we have done it. Okay, if you believe that that's what it turns into, now, does that help us? Well, this is 1 over k is like 1 over n, right? And 1 over k plus 1 is also like 1 over n because, look, each of these is growing 1 each time, right? So each of these are harmonic, aren't they? Yes? So the theorem says that, well, the theorem only works when? If they're convergent, right? And these aren't convergent. If this by itself is harmonic, it diverges. This one by itself is harmonic, it diverges. The theorem does not apply. You cannot split this into two separate sums. Which even if we did get that, even if we did misuse the theorem, we would have something that becomes infinite, right, that diverges, minus something that becomes infinite and diverges. What's infinity minus infinity? Don't know, right? It depends. So there's not a way that we can do this easily. So the way a collapsing or telescopic series will be handled is by starting to list out what the nth partial sum is. So imagine if I were to take this sum, I'm going to stop here. I'm going to say, let's investigate the nth partial sum. What we mean by nth partial sum is we're going to take the sum instead of k going 1 to infinity. I want to look at what the sum k goes from 1 to n looks like. So I'm taking not the full sum, but a partial sum. And I'm going to go out to the nth term. So what does this look like? What does the sum k equals 1 to n? Everyone see that's what I'm changing here? What does that look like of this? 1 over k minus 1 over k plus 1. So let's start listing out the terms. And make sure you have plenty of space to write horizontally here, okay? I'm going to give myself as much room as I can. Okay, plug in the first term. Plug in k equals 1. What would you get? 1 minus 1/2, right? Yes? Now, I'm not going to simplify that. Just leave it alone. Then I plug in 2, so I say plus. Now, here comes the second piece. What do I get there? 1/2 minus 1/3. Plus, and then 1/3 minus 1/2. fourth, and then I keep going with that, right? I keep going with that. And now I'm going to go the other direction, so leave yourself a lot of room here. What would the last term look like? What would the last one be? So I'm going to stop at n, right? So 1 over n minus 1 over n plus 1, right? That's what my last one looks like. What does the one before it look like? So what are you plugging in? If n is the last one you're doing, the one right before it would be whatever n is, take 1 away. So you said n minus 1, correct? So you're going to plug n minus 1 into this. Do y'all understand that? So plug in n minus 1. It's 1 over n minus 1. And then this one becomes, oops, I put plus. That's supposed to be minus. Then this one becomes 1 over n minus 1 plus 1 would be 1 over n. And if you want to, you could go back even one more term if you really want to see what's happening here. If I do, what's the one right before it? Before that one, I'm actually plugging in 1 over n minus 2. And then it would be minus 1 over what? N minus 1. Do y'all see why they call us a collapsing series? Do y'all see it? You don't need the parentheses, do you? This is all addition. So this negative 1/2 will cancel with that 1/2. This negative 1/3 will cancel with that 1/3. This negative 1/4 will cancel with the 1/4 that would be after that, right? And that would keep happening. Would this one cancel? This is an important one. Would this one right here cancel? What's the pattern? Okay, so let's talk about this, because this is a pretty simple collapsing series, all right? The ones that we're going to do in a little bit are going to be a little more complicated, so let's all get on the same page as far as notation. Would you agree that the second term in this first parentheses kills the first term in the next parentheses? All right, so this second one, I'll even say kills. All right, that's just a fun word to use. All right, this kills this off, right? And then this one is going to kill that one. And then this one is going to kill one that's there, right? We're not showing it, correct? So this one right here, does it get killed? By the one before it, right, that I'm not showing? So there's an arrow killing this one off. So that one is gone. And then this one kills this one, right? So those are gone. This one kills this one. Those are gone. This last one does not get killed off, right? It stays. And this first one does not have one before it that kills it off. So our nth partial sum k equals 1 to n of 1 over k minus 1 over k plus 1 will be equal to, what was that nth partial sum? 1 minus 1 over n plus 1. So it's that first one here, and then that very last one down there. Yes? That's what, oh, go ahead. How do you mean doesn't matter? 1 minus. Well, drop the parentheses here, right? Because you don't need them. So this is 1 minus a half, plus a half, minus a third, plus a third, minus a fourth, plus a fourth. So no signs are changing here, because the parentheses is only around these. I don't know if is that what you're saying? Okay. But this has to be a minus here. That needs to be minus because it is minus down there. Okay, that's the nth partial sum. We called this earlier when we first started talking about series. We called this right here capital S sub n. It's the nth partial sum. And then the actual sum of the series is what you get when you let n go to infinity here, right? What happens if I let n go to infinity here? That's what I'm looking for, right? Well, that's equivalent to letting n go to infinity here. And so you get what? 1. So this series, the series converges to 1. See, we're looking at the series. We're not looking at the sequence. So we're just like, you know what, geometric, we could actually tell you what the answer was, a over 1 minus r. Here with the telescopic, I can actually tell you what the series converges to. It's going to converge to 1. So I'm going to take the limit. I'm out of room here. The sum as k equals 1 to infinity of 1 over k times k plus 1. That was our original series, right? Before I did partial fractions, will be equal to the limit as n goes to infinity of 1 minus 1 over n plus 1, which is equal to 1. I hope that makes more sense. Let's go just a real quick backtrack through this. We looked at this, realized, hey, that might be telescopic. So we broke it up, partial fractions. We did an nth partial sum. The nth partial sum turned out to be this. We said, okay, if it's this, then take the limit as n goes to infinity, and that's what this is. And that goes to 1. All right, let's do another one of these. How about this? Find the sum k equals 5 to infinity of 1 over k squared minus 1. This is very similar to the problem that you were asking about in the homework, because I think in the homework it's 2 over n squared minus 1, and they start at 2. I'm going to start at 5. And you know what? I think just to match the book to see how you would handle it, let me use n instead of k. Because that might throw you off. I'm using k, the book's using n. So let's take a look at this. Is that, maybe you'll get into the habit of first seeing what happens to the sequence. What does the sequence do as n goes to infinity? The sequence right in here. Let n go to infinity, there, what happens? Get 0, which means that doesn't tell you anything, right? Okay, so I can throw that one out. Is it geometric? No, because the power is not in the exponent. Is it harmonic? No, because it's n squared, not just n. And then you start thinking, wait, n squared minus 1, that's n plus 1 times n minus 1, isn't it? Difference of squares. So you could rewrite that as sum n equals 5 to infinity of 1 over n plus 1 n minus 1. And then as soon as you see the two distinct linear factors, right, you do your partial fraction decomposition. And so this becomes sum n equals 5 to infinity of, in that partial fraction, you get negative 1/2 for each one, for A and B. So this becomes negative 1/2 over n plus 1 plus negative 1/2 over n plus 2. So from here to here, I'm just going to put PF for partial fractions. We okay with that? Should be an n minus 1. Right there, thank you. N plus 1, n minus 1 there. So now what I'll do is I will start listing out the terms of this sequence, right? Or this series. And I need to find the nth partial sum, right? And then take the limit at the end of it. The problem is that the book, the way they presented the problem, they're already using n. See what I'm saying? When I used k, all my stuff was k, 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 and then the last one was my nth term. Look, back here, I said, okay, let k be 1, blah, blah, blah. And then what was the nth term going to look like? This, right? Yes? And then I let n go to infinity. Here, you have to just be careful. You have to understand that n's already being used. So we're not going to really, it wouldn't make sense for us to talk about the nth partial sum with our dummy index being n. Yay or nay? Do y'all get that? Okay, because I can't write this down, right? I'm going to start at n equals 5 and stop at n. Doesn't make sense. So I need to use something other than n. So how about, I don't know, m? So I'm going to find the mth partial sum instead of the nth. So what would this sum look like? So I start at n equals 5. Remember, this right here is the mth partial sum. And then at the end of this, hopefully if I see some collapsing happening, I'll let m go to infinity at the end instead of n, right? Oh, by the way, they call collapsing. Do you see why they called it collapsing on the last one? Do you see that? It's like, if you think about it as like a bridge, right? The entire middle of this bridge collapsed out, and the only thing you were left with was the ends, right? And then they call it telescopic because the old school, like telescopes, the handheld ones, right? You pull them out like that, and you look, and then you put them back together, right? You know what I'm talking about? So everything, telescopes down into just the ends. That's where it comes from. Did you all kind of pick up on that, or no? It's just, okay. Makes sense now that that's the way they would refer to it. All right, here we go. This one's going to require, I think, quite a few terms to see a pattern. So, all right, let's plug in our first n. So n is 5. If I plug in n is 5, I have -1/2 over 6. And I'm not going to simplify that. I'm going to leave it alone. Maybe I should go with -1/2 over 6. And then I have plus -1/2 over 4. All right. Wait. Yeah, that's plus. That's okay. Next one. What's the next one? Oh, you know what? Hold on a second. I wrote something down wrong. Oops, copied my notes wrong. On my partial fractions, this one right here is +1/2. Everyone catch this right here? Change that to a +1/2, which would change this one, which would change this one. I'll highlight everything I changed. I accidentally looked at my notes wrong. We need things to cancel, and they weren't going to cancel. So that was -1/2 on top of the n plus 1, +1/2 on the n minus 1, and then here and then here. We up to speed? Okay. So now, what would my next term look like? Now I'm plugging in 6. So -1/2 over 7, and then plus 1/2 over 5. Okay, did anything collapse or cancel here? No, not yet, right? I mean, you can't, nothing. I don't even care about the numerators too much. I'm just looking for like 6, 4, 7, 5. I don't have anything that looks the same. But let's go one more out, and now we have what? -1/2 over 8 plus 1/2 over 6. Now that there we do have something, right? -1/2 over 6 and +1/2 over 6 would cancel out, right? Let's go write another one. -1/2 over 9, 1/2 over 7. Do we have another cancellation here? Yes, we do. This one right here. Do you want to write another one? Sure, I'll write one more. -1/2 over 10 plus +1/2 over 8, right? And this keeps going, doesn't it? But I'm out of room, so I'm going to have to continue on the next line. So I'm going to say plus ... And now let's take a look at what's happening at the end. All right, so I'm stopping. What's my last? What do I use as my last? Where do I end? I'm going to replace my ends with m, right? Okay, so let's go to the very last one, which I'm going to put way out here, because then I'm going to start building it backwards, just like I did before. So if I go to the mth term, m as in Mike, the mth term is negative 1/2 over m plus 1, and then plus 1/2 over m minus 1. We good with that? That's my last one. What's the one right before that look like? So you're going to plug in what right here for the one right before this? M minus 1 plus 1, so that's just m. So negative 1/2 over m, and then plus 1/2 over, you're plugging in m minus 1, then minus 1 again is m minus 2. I will put above these what we plugged in. We plugged in m here, we plugged in m minus 1, right? Just to remind you what I'm plugging in to this to get these things. I'm going to go another one. This time I'm plugging in m minus 2. So I'll have negative 1/2 over m minus 1 plus 1/2 over m minus 3. I'm going to go one more. It's just because I have the space, I may as well. Now I'm going to plug in m minus 3. I just want to really be sure I can see the pattern. M minus 2 here, m minus 4. And then it keeps going. All right, let's start talking about cancellation. I'm going to start from the beginning one here. Does anything out of this first set of parentheses cancel? Just the first guy, right? The first guy here cancels out with the second term, but 2 parentheses away, right? Will the first guy of the second parentheses cancel with anything? Yes, it'll cancel with the second one 2 parentheses away. So this will be gone, this will be gone, this will be gone, this will be gone. How about the first guy in the third parentheses? Yes, it'll cancel with the second one 2 away, right? It keeps doing that. So this one's gone. How about the negative 1/2 over n? Well, first ones, right, cancel with second ones 2 away. So is there a second one 2 away over there? We think so, right? So this one should go, because it's going to cancel with something over there. How about this one right here? It should go, because it's going to cancel with something over there. Oh, no, and then that last one. So look, everything over here, all the first ones are gone, aren't they? All the first ones? How about second ones? Well, think about it. Second ones, right? All the second ones we canceled from, what, the second one I canceled from the first one 2 in front of it, right? So look at this second one here. For it to cancel in this pattern, there has to be a first one 2 in front, right? There is no first one 2 in front. Do y'all see that? So this one is not going anywhere. I'm going to circle the ones that aren't getting killed off. This one's not getting killed off. How about this one? No, because there's not a first term 2 parentheses away, so it's going to stay. And then this one did, right? That one was the first one that actually had something in front of it, 2 in front of it. So I think that takes care of everything up there, right? Now let's come down here. And maybe we'll start from the back. How about this first one right here? How about that first one? Well, for first ones to cancel, right, you need to have a second one 2 parentheses further down the line, right, which you don't have here. So that one should stay. How about the first one in the parentheses in front of that? That would need to have a second one 2 parentheses away down to the right, which it doesn't. So it will stay. How about the first guy here? Now, it does have a second one 2 down, doesn't it? So this one does cancel with this one. How about the first one here? Yes, it does have 2 down right there. Oh, no, that's not 2 down. That's 1 down. Right there. And it cancels. What about this second one? It would need second one's cancel from the first one 2 away. So is there a first one 2 away? I didn't write it, but it's there somewhere, right? So this one right here will cancel with something over here, right? And then what about this one? Second one's canceled 2 in front, so we should have that. So this one should go away also. I'll draw it like that. Does this make sense? And when you take a step back, it looks like a big mess, doesn't it? But there's a lot of like just logic here, just thinking through like what the pattern of what's happening. So what is left here at the end of it all? I have 1/2 divided by 4, which is 1/8, right? I have 1/2 divided by 5, which is 1/10. That's not right? Hmm. 1/2 divided by 5 is the same as 5 over 1. Flip it, 1/5. Am I having like a complete brain fart, or are you all having a complete brain fart right now? What's happening? I don't trust my math right now. My mind's elsewhere. Is this okay? Yes? We have agreement? Okay, so 1/8 and 1/10. And then right here, I'm just going to leave that. That's plus negative 1/2 over m. And then the last one there, plus negative 1/2 over m plus 1. This is equal to the nth partial sum, right? The nth partial sum. If I add up m of these things, it will add up to be that. Now I want to let m go to infinity. And it's going to be pretty easy once you do that, right? If I let m go to infinity, this is a constant over infinity goes to 0, constant over infinity goes to 0. 0, so you get zeros there, right? And over here you have 1/8 plus 1/10. So add those up, that's your answer. So let m go to infinity, and what we get is the sum n equals 1 to infinity of the original problem, which was 1 over n squared minus 1. Yes, thank you. N equals 5 to infinity is, what was it? 1/8 plus 1/10? What's that? What is it? 9/40ths? Sounds good. It converges. Any questions? Kind of get the idea? The pattern going one way. Oh, you mean the pattern in the beginning and the pattern in the end? Oh yeah, it has. The pattern has to hold the whole way through for you to be able to start canceling stuff out. Are you talking about in here? Like this was the complete opposite of this? Will it always be that they are complete opposites? Is that what you're asking? Mm-hmm. Oh, will it always? It won't necessarily always be. It's the same pattern, though. Be careful in your wording. I don't want it to say yes if I'm saying yes to the wrong thing. The pattern is the same in the top and the bottom. It's the same. It's just the way you perceive it. And in the top, we were saying first one's killed, the second one's 2 away. Down here, we were saying the second one gets killed by the one 2 in front, right? The first one 2 in front. So it's the same thing, just saying it backwards. But it's the same pattern it's holding. It was right away. Yeah, I've seen problems with telescopic where you have to go out and maybe it's, first one is canceling, 3 or 4 away. I mean, you have to be prepared for that, but I've never seen it like in a book where it's more than like 4. Yeah. So you want to write out enough where you're really sure about the pattern. Let me see if there's one in here that I like. Yeah, let's look at this one. How about sum n equals 1 to infinity of natural log of n plus 1 over n plus 3. All right, so let's do a real quick check. Let's look at the sequence and see what happens when n goes to infinity. What happens right here if n goes to infinity? Infinity over infinity? But you can use L'Hopital's rule in that, can't you? And you get what? 1? Natural log of 1 is 0. So this thing goes to 0, which tells us nothing, right? The sequence goes to 0. So now we have to investigate the series. Definitely not geometric, definitely not harmonic, right? Because it's got the natural log in there. So I'm thinking maybe telescopic. Well, then I remember that there's a property of logs, right? There's a property of logs that says if you have a natural log and you have division inside, you can take that and split it into 2 natural logs with what between them? Subtraction. See, no partial fractions at all here was required. And now what I've done is I've created a difference. And look, for all telescopic series, you're going to have to create subtraction of 2 terms because that's going to give you the pattern of cancellation. If you can't split it into multiple terms, you're never going to get the telescopic to work. I'll show you that in this example when I'm done. What I'm getting at is if I don't split this and I just work with this and start writing out this terms, you won't get cancellation. All right, so look, let's do this. Let's start writing out the nth partial sum. So the nth partial sum will be equal to what? First term, natural log 2 minus natural log 5, right? Plus 4, yeah, 4. Then the next one will be natural log 3 minus natural log 5, and then plus the next one, natural log 4 minus natural log 6. Yes? And we just keep doing this. Let's see, do I need another one or do I have a pattern yet? Yeah, I'll just do one more. Natural log 5 minus natural log 7 plus. So it appears to me that the second terms kill off first terms, but 2 sets away, right? Well, 1 set away? How do you want to say that? Right next to it? Right next to it's here, maybe 1 set this way or 2. However it makes sense to you in your mind, all right? So the second ones kill off the first ones, but you got it as you move to the right. So let's look at this second one. Will this second one have one to kill off? Yes, this one will kill off with this, so these are gone. Will this second one, natural log of 6, have something to kill off? Well, it needs something down here, right? So that's going to work. I didn't write out the rest of them. I was just trying to show you this pattern, but I highly recommend you write out everything. So let's say down here plus, dot, dot, dot. Let's look at the last ones. What would they be? So I'm plugging what in? So the last one I'm plugging in m, right? M. So it'd be natural log of plus 1 and then minus natural log m plus 3. So that's what I get when I plug m into this. The one right before it would be ln m minus lm m plus 2. The one right before that should be ln m minus 1 minus ln m plus 1. Okay. What did we say? Second ones kill off first ones 2 to the right. Or 1 to the right. What do y'all think? 2 to the right? 2 to the right. Okay. So looking at this one right here, the second one should kill off the first one 2 to the right. The second one here, right? Does it have anything to kill off the second one here? No. Does not. Right? How about the second one here? No. Those stay. How about this first one here? The first ones are killed off by ones to the left of it. So this one right here should get canceled out by the one that was over here. How about this first one here? Should get killed off by something to its left. Something over there. Well, further down. Right? Up here, we never figured out what hung out here, what stayed. First ones get killed off by, or kill off by 2 in front. There is no 2 in front of that one, right? That's going to stay. How about natural log of 3? It's going to stay. And then everything else, I forgot to cancel natural log 6 here, but it's gone because we said it canceled with something over there. Natural log 7 over there, we never canceled, but it should cancel with something down there. Make sense? What's left then? ln2 plus ln3 minus ln m plus 2 minus ln m plus 3. Uh-oh. What's that? This is natural log of 2 is just natural log of 2. Oh, we want to let's let m go to infinity now, right? If we let m go to infinity, what we get is natural log 2 minus natural log 3, and then minus the natural log of infinity. So where does natural log go as you go to infinity? It goes to infinity, right? So I have negative infinity, take away, again, infinity, right? What does this mean? It diverges. This diverges. Because we said infinity minus infinity, we don't know, right? But negative infinity minus, minus infinity, again, that's a negative number. It's a huge negative number. So it's negative infinity, it's divergent. So this diverges. And that's okay. I mean, you can have a telescope or the bridge, the collapsing bridge, where the beginning is finite and the end is becoming infinite. The stuff in the middle is canceling itself out, but the thing at the end keeps getting huge. So it's going to force the series to diverge instead of converge. We good? What did I say I wanted to show you? What was I talking about? Oh, if you didn't break it up, okay? So let's say you had not broken it up, and you take this and you start looking at it, you know, what would happen? So if I had sum natural log n plus 1 over n plus 3, n equals 1 to infinity, and just start writing these things out, I would get natural log, plug in 1 first, you would get 2/4 plus natural log 3/5 plus natural log 4/6 plus, and you keep doing that, right? You keep going, wouldn't it? You wouldn't see the cancellation unless now you broke up these into natural log 2 minus natural log 4, plus natural log 3 minus natural log 5, plus natural log 4 minus natural log 6. You see that? Now I'm using that property, and now you can see that you would have that cancellation again. The second one here, because remember this is like in parentheses, the second one cancels with the first one, but 1 away. But if you left it just like this, you're not going to see any canceling. And each of these gets smaller, right? This is approaching 1. Natural log of 1 is getting close to 0. So they are getting smaller. They're not getting smaller fast. They're not getting small fast enough. So it's diverging. All right. I believe that that should hopefully resolve and wrap up this section. So I do just want to do a quick little summary of what we have. Right? We have what's called the Nth Term Test. The Nth Term Test says if you have a sub n going to somewhere converging to a constant c which is not equal to 0, or if a sub n diverges, then what can we say about the infinite series of a sub n? It diverges. That's called the Nth Term Test. So that was the thing that you want to start kind of doing. Like if you don't see it's geometric right away, or you don't see it's harmonic right away or something, then you want to just run this test real quick, almost like a visual thing, and you just say, okay, what happens is I let the sequence inside go to infinity, the n's or k's or m's, whatever it is. If it goes somewhere other than 0, you're done. You just say it diverges. That's the Nth Term Test. Then you have geometric. I'm not going to write it out again. After geometric, you have harmonic. And then you have telescopic. Right? Geometric series can converge or diverge, right? It depends on R. Harmonic, always diverge. Telescopic can converge or diverge. It depends also. And that one you have to just grind the answer out by finding the pattern. All right. Also remember page 441, theorem 8. Make sure you take a look at that. That just shows you again that if your series converge, you can add them together, you can subtract them, you can take a constant out. Okay, just make sure you're familiar with that. You don't want to start doing those operations unless you have that condition. All right, now we're going to get into 8.3. Your homework for that, you should do everything through 27 odd, and then maybe even try the evens. That was page 443. I had assigned, what, 7 through something before? Yeah. Odd. So go ahead and just, I would look at everything. I would look at 7 through 28, all. Practice. This is an important section. You get real familiar with the series here. Mostly everything we do from this point on is going to come back to one of these series. It's going to, we'll come to some conclusion, say, oh, and because it's like a harmonic, we, say it diverges. Okay, the next section. Eight 3 is what's called the integral and comparison tests. The integral and comparison tests, plural, okay? These are two different tests. So what we're getting at now is we have a series. We're going to be given a series, and we're going to be asked to figure out if it converges or diverges. And we're going to look at it, and we're going to say, well, it's not really harmonic, it's not really geometric. And so what we're going to do is we're going to say, we're going to use these tests to be able to determine convergence or divergence. So we're trying to handle things that aren't exactly cookie cutter like they were in 8.2. So let's talk about the integral test first. When you have a series, all right, when you have something like a sub n equals, or summation of a sub n, that's a terrible summation, sorry. I get real lazy with those summations. If you write enough of them in your life, you'll get tired of writing them too, and you'll just get lazy. Now, the assumption here is that n starts at 1 and ends at infinity. If I just write this, I said that last class. So that, if I were to look at this geometrically, I could say that I'm plugging in 1, right, and it's giving me some value a sub 1, and that's going to be a dot, correct? And then I'm plugging in some value 2, and I'm getting some other dot, that's a sub 2. Yes? And so we want to add these up. So I'm saying take the height of this. How high is that? How tall is that? A1. I want to add this height, which is A2. And then there's another one sitting out here, right? That's A3. I want to add all those heights up. Yes? Forever. Well, the integral test says that if you can look at your sequence as a function of real variables instead, then the function that would connect your dots together, right? The area underneath that should be what? Bigger than your sum? Right? If I add up A1, A2, A3, that would be smaller than taking that entire area, wouldn't it? So the integral test says something like, well, if the integral is finite, then this sum should be finite, right? Would you agree? If the total area under here is pi, then this sum should also be what, less than pi? Now, it's not going to tell me what it is, but it's going to tell me it is less than pi. So I'm not going to be able to get an answer, but I'm going to be able to determine whether or not I do have convergence or divergence. All right? That's the idea behind the integral test. So here's the actual test. Integral test. It says, we have some heavy conditions to be able to use this test. Here they are. Suppose a sub n is positive. What do we mean positive? Greater than 0, right? It's not going to give you negative values. Okay, so it always, all your dots have to be above like the x-axis, you could say. It's positive and decreasing. That's another very strong condition. And I'll add something to this. Eventually. What that eventually means is that your sequence might jump around a little bit. Now, everything has to be positive, all right? It might jump up, then down, then up and down, but eventually, after some place, from that point on, everything is decreasing. Remember, decreasing meant the one before it's taller than the next one, bigger than the next one, bigger than the next one. So it's decreasing, decreasing, right? Yes? And if it's positive, it's bounded below, isn't it? It's bounded below, and it's going to decrease eventually. So what's happening is they're getting smaller and smaller and smaller. All right, so that's what we need to start this, all right? A sub n is a positive decreasing eventually sequence. We let f of n equal a sub n. So what am I doing there? I'm defining a function f off of my sequence, right? So that I can look at it as a real valued function, because you cannot do integration on dots. You can only do integration on nice curved, continuous functions. So I'm converting my sequence into a function of real variables now. And now I have the results. If f is continuous on the interval 1 infinity, that means the function is defined and it goes forever and ever and ever to the right. And it's drawn without picking up your pencil. And if f is readily integrable, what that's going to mean for us is basically you can integrate it, all right? Then here are the results of the integral test. These are the main results. Then we have two things. One, if the integral from 1 to infinity of f of x converges. Now, we did these types of integrals earlier this semester, right? We called them improper integrals because one of the limits of an integration was infinite. So if that improper interval converges, that means goes to a number, the result of this says then the summation, the infinite sum, n equals 1 to infinity of a sub n converges. So I was trying to get you to see geometrically, is that if it converges, the area underneath the curve converges, the summation of the series, right? The infinite summations should also converge. That's the first result. And this one is not so obvious, I think. Maybe it is to you, but if that improper integral diverges, then, believe it or not, so must the series. I'm glad you said nice. Because you see how powerful this is, right? I mean, this not only, it's not like, okay, if the integral converges, great. If it diverges, I don't know. It's, if it converges, the series converges. If it diverges, the series diverges. So we won't have any gray area here. It's either going to or not. But the sequence has to meet these conditions, and that's where we run into issues. It's pretty strict conditions. All right. Let's see if we can apply it. All right. Here we go. Example. Does sum n equal 1 to infinity of n over n squared plus 4 converge or diverge? Am I asking you what it converges to? No, I'm just telling you one or the other. It's either convergent or divergent. So I start from the beginning. the nth term test. Nth term test says, look in here, let n go to infinity. What happens if you let n go to infinity in there? Infinity over infinity. L'Hopital's rule one time. 1 over 2n. So it goes to 0, right? 1 over 1 over infinity goes to 0. So that whole thing, the inside, the sequence goes to 0. What does that tell you? Nothing, right? So I'm going to put here, I'm going to take this one kind of slow. I don't want to just talk to it. On the nth term test, notice I'm writing out what it is I'm going to do. I'm taking the limit as n goes to infinity of n over n squared plus 4 by L'Hopital's rule. That's limit n goes to infinity of 1 over 2n, which goes to 0. So since a sub n goes to 0, test fails or is inconclusive, right? So these are the things, when you take your test, these are the things I need to see. You cannot get full credit on any problem on this test when it comes to showing convergence or divergence by getting it right by guessing. You can't be like, well, it's either converge or diverge, and you flip a coin, diverge. You know, you have to justify your answers. So most of the time, I would like to see the logic behind it. So showing the nth term test shows that there is some level of activity in your head as far as how to go about this, right? I tried this, it didn't work. How about geometric? I don't even need to consider it because I don't even see a power in the exponent. How about harmonic? Denominator is squared, it's not linear, right? How about telescopic? You would have to be able to factor the denominator, right, to create linear factors? Can't factor it, it's the sum of squares. If it was difference of squares, you could do it, right? And it might be telescopic and it might work. But it's intentionally n squared plus 4 so that you cannot do that. So nothing seems to be working at this point, right? So then we start going to our next possible test, which is the integral test. So I need to check a couple of things first, right? Integral test. If I'm going to do the integral test, I'm going to write down my sequence, n over n squared plus 4. Is this a positive sequence? I have to check these things. Is a sub n positive? Well, let's check. Do you agree that n over n squared plus 4 is greater than 0? Yes, I could verify it by multiplying both sides of this inequality by n squared plus 4, couldn't I? If I multiply both sides by n squared plus 4, that's the same as saying that n is greater than 0. Now, n is greater than 0 because I'm talking about a sequence, and we've always said n is going to start at 1 and go on from there, right? So that is true. I'm happy with that. So that is true. I do have a positive sequence. What's the other thing we need? We need it to be decreasing. So I'm going to say, so a sub n is positive. So I've got that taken care of. Now, I need to show it's decreasing. So what do I need to show? Want to show decreasing. How do I show something is decreasing? I show that a sub n plus 1 is greater than a sub n. That's how I show something's decreasing. Look, I'm telling you right now, if you get a problem that is supposed to be done by the integral test, and you do the integral test without showing these conditions, you're not going to get credit. You have to satisfy the conditions. This is part of what makes this whole thing a little weird, because it's the type of math you've never really had to do before, because you're having to justify each of your logical steps along the way. I mean, you're supposed to have done that before, but here more than anything else, we're going to have like 4 or 5 other tests, and all of them require their own sort of conditions. So when you do apply a test, you have to make sure they're all met. All right, so this is how I show. So what is a sub n plus 1? If you did your homework for 8.1, you should have done a little bit of this. This would be the sequence with n plus 1 plugged in. And then comparing that to the sequence without anything plugged in, just n. Right? That's what I need to show is true. That's a sub n plus 1. That's a sub n. You need to come to an inequality that you are happy with and that I'm happy with. I'm not happy with you saying that that's true. You need to show a little more than that. So what could you do here? To convince me that this is true. Can't pick numbers. Like try some different values of n? Yeah, you could make yourself feel better, but think about it this way. In math, just how do we prove something's true? If I were to define a function, this is a bigger thing. What if I defined a function to be, I'm just defining a function here right now. It's 1 if x is not 0 and 0 if x is 0. Okay, what does this function look like? At 0, it's 0, right? Anywhere else, it's 1. So if you were to take this function and you were to start checking its value at different places, right? Everywhere you'd start to see it's 1. So you would draw the conclusion if you checked how many values. 1,000, a billion, a jillion, a cajillion, doesn't matter, right? If you don't pick 0 and you pick all these other things, you're going to think it's 1. So at what point are you convinced it's always 1? After you've done how many? And then I come in here and I show you, nope, it's not. There's one place it wasn't. It's like the sun coming up tomorrow, right? Sun going to come up tomorrow? Just because it's come up, however many times you think it's come up, you think it's going to come up tomorrow? Is it guaranteed? It's not guaranteed. Same thing with this. If you plug in a few values, you can start to convince yourself of a pattern, but in mathematics, that is not a way to show something is true. To show it's true is to get it down to like we had a second ago. N greater than 0, that's something there won't be any debate about, because if you're saying n is greater than 0 and you're defining n to be 1, 2, 3, 4, 5, then there's no argument. Here, it's not like, it looks like it. We have to do algebra. So I'm going to multiply both sides. Well, how about I expand that bottom out on this side? So I'm going to square this mentally, expand out. I get n squared plus 2n plus 1, but I already had a 4 there, so that's this. Who was it who came by? And we did this, right? Yeah. So, I mean, it's just more of this. So I've expanded out. Now I'm going to multiply both sides of the inequality by this. So it'll cancel over here and it'll appear over here. I'll multiply both sides by this, which means it'll appear over here and cancel over here. So I'll have n squared plus 4, n plus 1, and then n times the other denominator. Now I can only do that if I can promise you that these denominators weren't negative, right? But you can again check. This will never be negative as long as n is greater than 0. And this will never be negative as long as n is greater than 0. So that was okay to do that. And now expand these out. You get n cubed plus n squared plus 4n plus 4. On the other side, n cubed plus 2n squared plus 5n. And now we get some cancellation. N cubes are gone. That's about all, right? Let's move everything to one side. Yeah, I just realized what I did. Do y'all see what I did? It's not going to be this, right? Well, let's draw, but what did I put up here? I have to show it's decreasing. What did I do here? This is increasing. right? Look, this is increasing. The n plus 1 one is bigger than the one before it. So let's save ourselves because of time. Can I just flip the inequality over, please? Because that's not what it means to be increasing. It's back. I have it backwards. No one saw that in the beginning? All right. Decreasing means that the one, n plus 1, the one coming next, is smaller than the one before it. Other than that, everything's still the same setup. All right, now I'm happy to work with this. Okay, so let's move things around. How do we want to do this? How about we move everything to the right? We'll get a 0 over here. How many n squareds will we have? We're subtracting n squared on both sides, right? So we'll get just 1 n squared. How many n's? Get 5n here. We take away 4n. We get just n. And then do we have a number? Minus 4. Is n squared plus n minus 4 bigger than 0? Try n as 1. Does it work? It doesn't work, does it? How about n is 2? N is 2, it'll work. N is 3, it'll work. So maybe this is another way that you could look at it that might help you. Because you have to convince yourself, all right, and then me. How about this? N squared plus n. Leave that 4 back on the other side. When will this be bigger than 4? Well, when n is 1, it's not bigger, right? But when n is 2, you're there. When n is 3, yes, you're there. How about this? How about if I leave that and I factor the right side, pull out an n? This is, if I plug in 1, it's 1 times 2, that's not going to work. But when I plug in 2, it's 2 times 3, that does work. Plug in 3, that's 3 times 4, that does work, right? So you have to get it to a point where you can say, yes, this is true, but what? For n greater than or equal to 2. And do you remember when I said that the integral test works if your sequence is positive and decreasing eventually? This is the eventually part I'm talking about. It wasn't decreasing right off the bat, but eventually it was decreasing. Yes? All right. We have met the conditions. We have met the conditions. Yes? Well, almost. Now we have to go and convert this sequence to a function. Let's let f sub n equal n over n squared plus 4. I'll go back to our we had a positive decreasing eventually sequence. We had that. I'm now defining my function to be the sequence. I want to check that it's a continuous function on the interval. And it's readily integrable, meaning you're going to be able to integrate it. So now I'm going to come back over here. Is this function continuous? F continuous on 1 infinity? Yes or no? Well, it's a polynomial divided by a polynomial, right? All polynomials are continuous everywhere. The only thing I have to worry about is if there's ever like a division by 0. But n squared plus 4 can never be 0, right? So this is a continuous function everywhere. So definitely continuous on 1 infinity. Is it readily integrable? Can you integrate that? I hope so. We're about to find out. So we're ready to go. Let's do the integral. I'm going to integrate from 1 to infinity. It's okay. Remember how we said for n greater than 2? It's okay if we do 1. Doesn't matter. We could go to 2 also. It's not going to hurt us. The idea is that a finite number of terms in a sequence has no effect on whether or not it converges or diverges. That's an important thing. I'll probably write it out in a little bit. But if I tell you, I'm going to do it over here off the board. If I tell you I have a sub 1, plus a sub 2, all the way out forever. If I tell you that this thing goes to infinity, then do you think that if I cut off two of them, it's going to change that it goes to infinity? No. What if I tell you this adds up to be some number without telling you what the number is, right? And then I say take a couple out. Is it still going to add up to be a number? Not the same number, but a number. Yes? So taking a finite number of terms out of a series has no effect on the divergence or convergence, as long as it's finite. Now, it affects the actual value if it converges, but it doesn't affect the actual fact that it converges. Yes? Okay. But it has to be a finite number. So that's why changing this integral from 2 to infinity, look, if it converges, it converges. If it diverges, it diverges. No big deal. All right, let's try and integrate this. I'm going to keep it as n, which means that when I have my d out here, I need to say dn, because my variable of integration is n. You might want to just use x in the whole thing if that makes you happier, if it makes you feel warm and fuzzy inside, if you like x that much. But there's no problem with using n. Technique of integration here. Basic u sub. U is equal to n squared plus 4. The derivative of that is 2n dn, right? You're off by 2. So bring a 1/2 out. And rewrite this integral. How can I rewrite the integral? 1/2 came out, and then don't put the negative 1 to infinity now. Don't even worry about the integral. We're going to switch it back, and then I'll do the limits of integration. Because we're switching variables, the limits of integration don't always stay the same. 1 over u du. What is the antiderivative of 1 over u? Natural log, so I have 1/2 natural log u, right? Plus a constant, but I'm not worried about that because this is a definite integral. So now let's switch back. It's 1/2. What's u? N squared plus 4. And now I can say evaluating from 1 to infinity. What do we get? We get, yeah, infinity in there is infinity, right? And then minus, what do we get when we plug in 1? Some number, right? Some number. What's infinity minus a finite number? It's infinite. That means that this integral does what? Diverges. So the integral diverges, the series diverges. Therefore, sum n equals 1 to infinity of n over n squared plus 4 diverges by the integral test. I have 10 minutes. I want to show you the beginning of something of another problem that we could use integral test on. I don't think I'll be able to get through the whole thing, but this has something very interesting happening in it. Any questions on that, though? All right, so next example. Let's try and find sum n equals 2 to infinity of 1 over n natural log of n squared. And then the question is, determine convergence or divergence. I'm abbreviating. Determine the convergence or divergence of this series. What would be the first thing you would do? Nth term test. Let n go to infinity. What happens to this? That goes to 0, right? So I could say something like nth term. I know that a sub n goes to 0, so this fails. I'm just summarizing it, but I'm letting you know that I did think about it. Right? Is it geometric? I don't see powers in the exponent. I mean, I don't see the n in the exponent anywhere. Harmonic, well, 1 over n's harmonic, but then all this crap's here, so that screws it all up. Telescopic, well, telescopic relied on me being able to like split it up, partial fractions, or we got lucky that one time it was the log and I could use the property, but this does not look like it's going to happen. So then I start thinking integral test, but then if I'm going to do integral test, I'll have to be able to integrate it, right? I didn't really point that out in the last problem because I knew it would integrate easily. But this one, you should probably start thinking, if I'm going to use integral test, I better be able to integrate it. So I look at this and I say, hey, look, if I let u be natural log of n, the derivative is 1 over n is right here. So I have a u du right there. I will be able to integrate that. So I'm thinking integral test now. But it has to satisfy all the conditions. So here comes integral test. The first condition we need is what? A sub n must be positive. Let's go ahead and check that. Is 1 over n natural log n squared greater than 0? Well, kind of. The denominator can actually be 0 if n is 1, can't it? Look at this. What's natural log of 1? 0, right? And that's not a problem because where does my series start? Start at 2. So we're avoiding it. So as long as n is greater than 2, this is well defined, and then I can multiply both sides of the inequality by the denominator. This is a positive number, that's a positive number. When I multiply both sides of it, what do I get? When I multiply both sides by this denominator, what do I get over here? 1 is greater than 0, is that true? Yes. Okay, so it is definitely a positive sequence of numbers. Now I need to check that it's decreasing. So I want to show, and let me get this shit straight this time. I want to show, I'll write it a little different. I want to show that the nth term is bigger than the next one. Doesn't that mean decreasing? The one in front, nth term, is bigger than the next one, which means that it's getting smaller as you go. All right, what is a, or 1 over n natural log n squared greater than 1 over n plus 1 times, natural log n plus 1 squared. Wow, this does not look fun. Now, the reason I'm showing this, and I'm almost out of time, but there's something, I mean, we could start messing with this, right? Multiply both sides. I want to see how messy this gets, see if we want to surrender to it or not. And then I'll show you the whole reason I wanted to bring this up. I multiply both sides, right, by this, and then both sides by that. And basically, it's like, some people call it cross multiplication. I don't like to call it cross multiplication. You get this statement. See, the problem is this. You can convince me that n plus 1 is bigger than n. That you can convince me of. I don't have a problem with that. But you need to be able to convince me that natural log of n plus 1 squared is bigger than natural log of n. That I'm not as confident about. So here's the approach I wanted you to see. I mean, you might sit here and go, I'm kind of stuck on how I can do that. So think about it this way. If I tell you that I have a function, okay, not a sequence, a function, and I tell you it's decreasing, it means it's going down, right? If I look at a function that's decreasing and I look anywhere on it, and I look at the the derivative, which would be the slope of the tangent line, that derivative should be what? Positive or negative? Should be negative, right? If you have a function decreasing, the derivative is negative. So what I'm going to do is, instead of trying to show this inequality is true, I'm going to look at this sequence up here as a function, and I'm going to show you that its derivative is negative. If I can show you that the derivative is negative, I show you that the function's decreasing, which means the sequence is decreasing. It's a different approach to showing the same thing. So here's what I'll do. I'm going to let f sub n be equal to 1 over n times natural log n squared. I'm going to find the derivative of this. And I think what I'll do is quotient rule. What is the derivative of the top? 0 times the bottom, which I'm not going to write. Okay, that's the bottom. It's all going to go away, right? Minus the derivative of the bottom is the next part of quotient rule. So you have to take the derivative of this, which includes a product rule in it, right? It's n times this, and that requires chain rule. But we're in Cal 2, right? So this is just a derivative. So the derivative of this would be derivative of n, which is 1 times natural log n squared, then plus, doing product rule, derivative of natural log of n squared would be 2 natural log n, then chain rule, derivative of natural log of n, 1 over n, finish off the product rule, times n, they'll cancel each other out. All of this over what? The bottom squared, right? That's your quotient rule. All of that squared. Okay, sorry. I've got to see what that is. What am I trying to show? That thing is negative, right? Let me just see what this says real quick. Okay, she seems to be doing okay. Okay. I want to show this whole thing's negative, right? That's all. And if I can show that, it's decreasing. So this is 0, so I don't care about that. How about the bottom? You know, this is a positive number. Natural log of n could be negative, right? Natural log is negative somewhere, but I don't care. I'm squaring it, and then I'm squaring the whole damn thing, and so that's all positive. This whole thing on the bottom is positive. Not worried. That's 0 up here, minus. Now, natural log of n, again, it could be negative, but I'm squaring it, so that's positive. Plus, this is 2 natural log of n, and then that's a 1. So I just need to make sure that this right here is positive. Do you all agree? So remember the restriction on n. N must be bigger than 2. So if you go look at the natural log function, that's 1, right? So at 2, it's positive. So that's all a positive number. This is all positive. So you've got minus a positive number plus a positive number, and then all over a positive. So this is going to be a negative number up here divided by a positive number, which is going to be negative. So this whole thing is a negative number, which means your derivative is negative, which means your function is decreasing, which means your sequence is decreasing. Yes? That's just one of the tools we can pull out when we're trying to show a sequence is decreasing. Turn it into a function, look at its derivative. Now, you won't always want to do that, but it's there. All right, well, I'd leave the rest to you. We've shown all the conditions, right? So you just need to go integrate that. This time, you would need to go from 2 to infinity. You would not go from 1 to infinity because it's not defined at 1, right? Okay, let me get back to my office. I will send out an email today with your homework assignment because I have to pick these very carefully so that they don't have any of the other tests that we haven't done in them, all right? That sound fair? All right, everyone, I'll see you on Thursday.